Good evening, Lamai. Today we are going to discuss about the calculations in Moline redox reactions. Right? Before we are going to discuss about the calculations, first we should know to predict whether a reaction will occur or not if two chemicals are to mix together, or if some reagent is added to a flask containing some chemicals. Right? Let's discuss how to select whether a redox reaction will occur or not when some reagent is mixed to a flask containing some chemicals. Right? So the idea is this, right? So first we are going to discuss about things like this. So let's consider that we are with a flask like this and containing some Fe2 plus and Fe3 plus ions in it. Say you had taken 25 cubic centimeters of this thing, right? Now you are supposed to come up with the concentration of this stuff, concentration of these two guys, right? So first what we are doing, so first we assign the values as x moles and y moles, right? Then say that some Km of a solution is added to this thing in acidic medium, right? And say that 25 cubic centimeters were consumed of 0.1 molar concentration. So first thing here we are going to discuss is actually which reactions will occur, whether the KMnO4 reacts with the Fe2 plus, whether the KMnO4 reacts with Fe3 plus, or with both, or with none. Basically there should be a reaction, right? So KMnO4 will react with Fe2 plus or Fe3 plus, or with both the stuff, right? So first we are trying to get some idea how to select which reactions will occur and which are not going to occur, right? That is our first consideration here. So to get that idea, get that clear idea about this thing, right? First of all, we need to know some specific oxygen states shown by some chemicals, right? Let's come up with that thing. First of all, let's discuss, go to that, and then we can solve for this question, right? Okay, so
recording in progress.
Right, let's come to this page, Lama. This is actually page number 35 in your tube, right? So you see this thing appearing here, the redox reactions. So with this special note, we are able to discuss what are the specific oxygen states shown by these special elements, right? Let's discuss about that thing, right? So basically, when it comes to S block elements, those are not showing any variable oxygen states. What are the S block elements? At the group 1, you are with lithium, sodium, potassium, rubidium and cesium. Those are the group 1 S block elements. What are the group 2 guys? Beryllium, magnesium, calcium, strontium and barium. The thing is, actually those guys won't show variable oxygen states. That means when it comes to group 1 elements, they are always showing the +1 oxidation state, right? When it comes to group 1 element, right, they always show the +1 oxygen state, right? When it comes to group 2 elements, they always show the +2 oxygen state, right? So no variable oxygen states appearing with the S block elements, right? That means in these redox reactions, S block elements are not going to participate if those are with +1 or the +2 oxygen states at the initial state. That means, let's see, if you are with potassium permanganate, let's consider that example which we have discussed earlier, right? With that example, you had added acidic medium, right, KMnO4. The KMnO4 means this is a combination of K plus and the MnO4 minus sign, right? This first rule says, if you think of a redox reaction happening with the KMnO4, this first rule says actually no need to consider about the K plus. No need to consider about the K plus. Why is that? Because as a group 1 element, potassium always shows the plus 1 oxygen state only. There's no other oxygen state available with the potassium, right? So that potassium is not going to participate in redox reactions. K plus is not going to participate in redox reactions, right? No other oxygen states available. So when considering reactions with H plus KMnO4, K plus is not going to participate in such reactions, right? If you need another example, right? Let's discuss about this thing, right? Consider this one. So you have a flask and you are adding from the top some acidic medium potassium dichromate, K2Cr2O7, and say you are with some sodium chloride and some let's say some magnesium sulfide with you, right? This first rule says, right, as S block components, this K plus, magnesium 2 plus and the Na plus, right, as well as the K plus. Here you have the K plus ion and the Cr2O7 2 minus ion. So this first rule says, right, this S block guys, this one as well as this one as well as this one, these guys are not going to participate in any kind of a reaction here when considering redox reactions. No redox reactions happening with the group 1s or group 2s, right? That is the first rule here, right? So you should know these rules, right, to select whether a reaction will occur or not, right? Okay, right. Let's come up with the second example, right? Let's come up with the second example here, second point, right? Basically, if you think of these special elements, if you think of these things, right, aluminium in these reactions always show the +3 oxygen state. Aluminium could appear as the 0 oxygen state. Other than that, only the +3 will be shown by aluminium. When it comes to zinc, it will show only the +2 oxygen state other than the 0 oxygen state. When it comes to lead, it shows only the +2 in these redox reactions. For tin, it could show the +2 as well as +4. When it comes to iron, it could show them +2 and +3 as well, right? These are the specific oxygen states available with some special metals, right? Other than the 0 oxygen state, aluminum shows only the +3, zinc shows only the +2, lead shows only the +2, tin shows +2 and +4, and iron can show the +2 and +3. No other oxygen states will be available with these elements, right? That should be known to select when selecting these redox reactions, whether that will occur or not, right? Okay, next one, right? Next case, the third one, halogens. What about halogens in redox reactions, right? Let's consider the halogens in your redox reactions, right? When it comes to halogens, right, in redox reactions, halogens will always come up with X minus form or the X2 form as products. Halogens will always come up with X minus form or the X2 form as your products, right? What this says, it is like this, Lamai. So let's see. Let's think of this kind of a situation, right? So you are with some Cl minus ions in your solution. You are with some Cl minus ions in your solution, right? Cl minus means you are with the minus 1 oxygen state, right? Let's say from the top you are adding some oxidizing agent. You are adding some oxidizing agent. So if you are to add some oxidizing agent, right, halogens should get oxidized, right? Right? Right. So the halogen is possible to come up with some oxidation state here as you have added some oxidizing agent, right? So this rule says, okay, this halogen, the Cl minus will oxidize, but to where? To the X2 form, not to any other oxygen states, to the X2 form, that Cl, chlorine, will get oxidized. That is what it says, right? So in redox reactions, halogens always tend to form the X minus form or the X2 form. If you need another example, right? So let's say you are with, right, some Cl2 here, and you are adding some acidic, some reducing agent or something, from the top. That means the things at the flask should get reduced by this addition, right? So to where this guy will reduce, according to this rule, it says, right, this halogen will get reduced to Cl minus form, So only the minus 1 and the 0 oxygen states are available as products for the halogens. That is the point there, right? Okay. So halogen will get reduced to minus 1 oxygen state here by reducing agent, right? So that is the idea, right? So if halogens are available as products, so those will always come up as X minus form or the X2 form. That is what this point says, right? Clear, no? Right. So it could be, right, so if you need some other example, right, so I'll come up with some other, right? Let's say you are with OCl minus, right, and you are adding some reducing agent here from the top, right? So what will happen? So in this case, this chlorine is with plus 1 oxygen state, right? You can calculate that stuff, no? Right? As a reducing agent is added, so chlorine should reduce its oxygen state. So what will happen? So basically, this chlorine will reduce to the X minus form or to the X2 form, right? Normally goes to the nearest oxygen state available. So plus 1, then the nearest is the zeroth oxygen state, so it will go to Cl2 form, right, where the oxygen state is 0, right. So that is what this says, right. When you are to add some reducing agent or oxidizing agent, halogens always supposed to come up with the X2 form or the X minus form. Even with the iodine, the same things will happen, right. That is the idea about the third point, right. Clear? Right. Let's discuss about the fourth thing, right, the manganese containing, right. The fourth point is about manganese containing stuff, right. Okay, let's consider this example. I'll give you some example right here. So it is like this. See, let's come up with the first example there. So we had Fe2 plus and the Fe3 plus in our flask, right. What we have done was actually add in the acidic medium KMnO4, right. Okay, so let's try to come up with the reactions here. So basically, so H plus KMnO4 means you are with acidic medium K plus ion and the MnO4 minus ion, right. What we know is actually this K plus is not going to react in a redox reaction. It is a S block species. S block species won't react in redox reactions, right, in these chemical calculation questions, right. What about the MnO4 minus? What about the MnO4 minus? Right? This rule says the MnO4 minus in acidic medium, what happens? MnO4 minus in acidic medium, right, always reduced to Mn2 plus, always reduced to Mn2 plus. So we can write the MnO4 minus here in acidic medium always tends to reduce to Mn2 plus. That you should know, right? Some reduction will occur towards Mn2 plus, right? Okay, so that is the point, right? If MnO4 minus is involving in reaction, if you have added MnO4 minus, right, in acidic medium, only a reduction could occur and it is towards the Mn2 plus. It is towards the Mn2 plus, right? Okay, so even with the MnO2, if you had an MnO2 from the top, still you are supposed to come up as the Mn2 plus, right? Mn2 plus, right? So in acidic medium, if you had used some manganese containing species, definitely those guys will reduce to Mn2 plus. That is what this point says, right? Okay, all the manganese containing species in acidic medium always reduce to Mn2 plus in redox reactions, right? Okay, then what about the basic medium considerations? What about the basic medium considerations, right, in manganese containing species, right? So it is like this, right? Just think of adding some, right, sorry, just think of adding some MnO4 minus in basic medium. It is MnO4 minus in basic medium, or the K plus K MnO4 in basic medium, right? So according to this theory, this point, it says what? If in basic medium KMnO4 is undergoing a reaction, this theory says it will always reduce to Mn2 plus, sorry, MnO2, sorry, the MnO2, right? KMnO4 in basic medium always reduces to MnO2, right? If a reaction is occurring, always reduces to MnO2, and you know that K plus is not going to react now, no? This dog guy, no? So in basic medium, MnO4 minus always reduces to MnO2, right? Clearly, right? Keep that in mind, right? Okay, that is how the manganese containing behave in redox reactions in basic medium, right? This is a kind of a redox reaction, it's a reduction, right? It's a reduction. Right, no? Okay, the idea is clear. Right. Let's consider the next one. Right, let's consider, right, the next stuff, the chromium containings. The chromium containings, right? How these chromium containings behave, right, in redox processes, right? Right, that is our next consideration, right? So when it comes to chromium containing species, right, in redox reactions, if you are considering the acidic medium, right, chromium containings always reduce to Cr3+, always reduce to Cr3+. In acidic medium, always reduce to Cr3+, right? The idea is clear, right? So if you need an example, right, let's say you have this kind of a flask and some reducing agent is available, right, and you are adding some acidic medium sodium dichromate, then what should happen to the chromium containing species here? So as we know, the S block guys won't participate in redox things, right, here. And then what about the chromium containings? The chromium containing guy in acidic medium always tends to reduce to Cr3+, right? It's a reduction, right? So that is what this rule says. It could be either the dichromate ion or it could be the chromate ion. Anyway, if it is reacting in an acidic medium, always chromium containing tends to, right, come up as Cr3+, right? That is what this says, right? In an acidic medium, chromium containing always come up as Cr3+, kind of a reduction occurring there. So if you have to think of the oxygen state available here, you can clearly see that reduction, right? See, what is the oxygen state here? This guy come up with plus 12 divided by 2 is plus 6. So here the plus 6 reduces to plus 3, kind of reduction. Here also the plus 6 reduces to plus 3. So kind of reactions are happening, kind of reduction reactions are happening with the chromium containings in acidic medium, always towards the Cr3+, right? The idea is clear, right? Let's discuss about the chromium containings in basic medium, right? If you have to think of these chromium containings in basic medium, right? Right, in basic medium, chromium containings always prefer chromates in basic medium, right? The Cr3+ oxidizes to chromates, right? So that is what we are predicting for chromium containings to happen in a basic medium, right? Okay, right. Let's discuss the oxalate situation. This is about the oxalates, how they react in redox reactions, right? See, like this, right? I'll give you some example, right? What will happen with the, right, oxalates, right? So let's say you are with some sodium oxalate in your flask. Here is some sodium oxalate in your flask, right? So from the top, you are adding some oxidizing agent. From the top, you are adding some oxidizing agent. We'll discuss what kind of reaction could occur here, right? As S block guys are not involving in these reactions, right? So what could happen with the oxalate? So this is actually, you have two of Na plus ions and C2O4 2 minus ion, right? So here the C2O4 2 minus ion is the one to get oxidized. So if you are to add some oxidizing agent, the C2O4 2 minus will get oxidized to CO2, that gas. Always the oxalates will get oxidized to CO2. That is what this says, right? In a redox reaction, if you had come across the C2O4 2 minus situation, that ion, oxalate ion, always that tends to get oxidized to CO2. Keep that in mind. That is what this point says, right? Oxalate get oxidized to CO2 when an oxidizing agent is added. When oxidizing agent is added, right? So oxalates will get oxidized to CO2, right now? Okay, that is about the oxalates, right? Okay, let's now discuss about the sulfur containing redox reactions. Sulfur containing redox reactions, right? Okay, so when it comes to sulfur containing, right? So sulfur is with variable oxygen states like this. Sulfur containing are with variable oxygen states, right? So -2 to +6, you can see the oxygen states appearing with sulfur containing, right? So as an example, for the -2 oxygen state, right, H2S and S2 minus, those two can be considered as some examples for -2 oxygen states. For the 0, sulfur is the example. So if the sulfur is going to oxidize to +4 oxygen state, so the SO2 or SO3 2 minus are going to be the products. If sulfur containing the sulfate, so those will oxidize to sulfate, right? So normally in chemical calculation questions, sulfur containing tends to get oxidized, not to reduce but to oxidize, right? So this is how the oxidations occur. The -2 oxygen state will oxidize to 0, right? The 0, if you are starting with 0 sulfur, right, that guy will oxidize to +4, right? And if you are starting with +4 sulfur, that thing will oxidize to +6, right? That is how the sulfur containing will get oxidized in redox reactions. Normally, we won't see the reduction of sulfur containing in redox calculations, right? Normally, some oxidations we would observe with the redox calculations, right? And keep that in mind. Normally, the even numbered oxygen states are available with the sulfur, right? -2 is there, then 0, you don't have +1, you don't have +1, +1 is not there, +1 is not there, right? So +3 is not there, right? You don't have -1, you don't have -1, right? You don't have -1, -1 is not there, +1 is not there, right? +3 is not there, +5 is not there with the sulfur. So normally sulfur tends to form the even numbered oxygen states, right? Keep that in mind. So +2 is there, but we won't see that thing appear in chemical calculations, right? +2 oxygen state appears, +2 oxygen state appears with the sulfur, right? That is there, but we won't observe that thing in chemical calculations. So in chemical calculations, what you should know is these oxygen states, right? If sulfur is going to get some -2 product, that is definitely the H2S or the S2 minus. If sulfur is going to give you a 0 product, that is sulfur. If sulfur containing is going to give you a +4 product, that is SO2 or SO32 minus. If sulfur containing is to give you a +6 product, it is definitely the SO42 minus, right? So that is how the sulfur containings will participate in redox reactions. Always you could see some oxidations happening with that, and always they tends to come to the closest oxidation state possible. -2 always oxidizes to 0. 0 oxidizes to +4 and +4 oxidizes to +6, right? If they have not mentioned, don't oxidize the -2 to +4, right? Always oxidize the nearest oxidation state possible, right? That is what we are supposed to do with the sulfur containers. I'll do some examples, right, to get some idea. So first let's go to the points here, right? So that is the idea, right? And next point, it says, right, as a reactant, diluted H2SO4, diluted SO42 minus. Diluted SO42 minus is without any redox property, right? That is what it says. So you clearly see when it comes to SO42 minus, right? From there is no arrow starting from. There is no arrow starting from. So that means SO42 minus can be obtained as a product in these redox reactions, but it is not going to participate in redox reaction as a reactant if diluted SO42 minus is used, right? In this situation, SO42 minus is not with any redox properties. Diluted situation, right? In concentrated situation, you can think of such reductions happening, but with the diluted conditions, SO42 minus is not going to give you any kind of product, any kind of reaction won't occur. Redox reaction won't occur with diluted SO42 minus, right? So SO42 minus is able to participate in precipitation reactions, right? But not in redox reactions if you are considering the diluted situation, right? Okay, that is what it says, right? As a reactant, diluted SO42 minus is without any redox property. So no oxidation, no reduction with dilute SO4 as a reactant. So because of this, dilute SO4 is used to acidify redox reactions, right? Because of this, dilute SO4 is used to acidify redox reactions, right? Okay, normally to acidify the redox reaction, to supply the acidity, to supply the H pluses in your redox reactions, right, we use the dil H2SO4. Dil H2SO4 is used to acidify redox reactions, right, to supply the acidity, the H pluses in your redox reactions. Normally H2SO4 is used because the diluted SO42 minus is without any redox property, right? Got the idea, right? So with this knowledge we have gathered, let's try to think of how the redox reactions are to occur, right? How to decide whether a reaction will occur or not. Let's try to predict with the use of this knowledge, right? Okay, so let's go to this. This is what we are trying to focus now, right? So right, no? Okay, let's discuss about this thing. Right, so what this says is like this, Lamai. So this is the first idea, right? I'll write this one here. So let's come to the board and to give you some idea here, right? Okay, the idea is this, right? Let's say you are with a flask with Fe2 plus ions and Fe3 plus ions, right? You are with a flask with Fe2 plus and Fe3 plus ions. right? Okay, so that is with X moles, no worries, right? X moles, and this is Y moles, right? Let's say from the top you are adding acidic medium KMnO4, that means the K plus and the MnO4 minus. Let's try to discuss about the reactions which could occur with this setup, right? So let's try to predict. The idea is this, right? First of all, right? First of all, think of the reagent you are adding from the top, right? First of all, think of the foreign reagent you are adding to the flask, right? When thinking of the foreign reagent you are adding to the flask, right? The K plus as a S block ion, it won't participate in any kind of redox reaction. K plus as a S block ion, it won't participate in any kind of redox reaction. Then, with the knowledge what we have gathered, what we can say. So when it comes to manganese containing in redox reactions, right? In acidic medium, MnO4 minus always tends to get reduced to Mn2 plus. Always tends to get reduced to Mn2 plus, right? So MnO4 minus get reduced to Mn2 plus, right? So then, how to select which guy will react here? So the idea is this: if there is a reduction occurring here, definitely you should observe oxidation at the flask. Definitely you should observe an oxidation at the flask. So this guy to get reduced, definitely, right? Some electrons should be released by these species. So if a reduction to occur from here, definitely there should be oxidation at the flask. That is logical, no? Right. Okay. So now we are supposed to select which species are to get oxidized here. We are supposed to select which species are to get oxidized here. The point here is, right? If some chemical species is with its highest oxidation state available, then such a species can't get oxidized. Can't get oxidized. Is this idea clear? The idea is lamine, right? Oxidation means you are trying to increase your oxidation states. Oxidation means it is actually increasement of your oxidation state, right? So if you are with the highest oxidation state available, then you don't have any other oxidation state to increase your oxidation state. So you are with the highest oxidation state of you, so that you don't have any other oxidation state available to increase your oxidation state. That means, right, you can't participate in an oxidation. Right? That is what it says. If some chemical species is with its highest oxidation state available, then such a species can't get oxidized. So if you think of these ion guys appearing here, the Fe2 plus and Fe3 plus, what we have learned is actually the ion can have only the +2 or the +3 oxidation states. So when considering the Fe3 plus, it is the highest oxygen state available for Fe. It is the highest oxygen state available for Fe. So you can't think of a oxidation from Fe3 plus. You can't think of a oxidation from Fe3 plus. So Fe3 plus is not going to participate in this reaction. So Fe3 plus is not going to participate in a reaction here, right? The idea is clear, no? So we can say, right, Fe3 plus won't get oxidized, won't get oxidized. Fe3 plus won't get oxidized as it is with the highest oxygen state available. But what about the Fe2 plus? But yes, Fe2 plus here could get oxidized, right? So Fe2 plus here will oxidize to come up as Fe3 plus. If you are not with your highest oxygen state, then you can get oxidized, no? So Fe2 plus will oxidize here. So what are the two half reactions available here, or what is the chemical reaction possible with this setup? What is the chemical reaction then possible with this setup? So it is going to be, right, we can write the chemical reaction possible with this setup as, right, so your MnO4 minus in acidic medium, your MnO4 minus react with the Fe2 plus here to produce what? The Mn2 plus, and this guy will reduce to Mn2 plus, and the Fe2 plus will get oxidized to Fe3 plus. So this is the redox reaction or the redox change happening with this system, right? Got the idea how to decide which species are to get reacted, right? Clear, no? Let's come up with another example. Right? Let's come up with another example. Right? Okay. See, you are with a flask with SO3 2 minus and SO4 2 minus with it. You have some X moles here, okay, Y moles here, no worries, right? And let's say from the top you are adding some acidic medium dichromate Cr2O7. So sorry, let's take it as potassium dichromate, acidic medium potassium dichromate K2Cr2O7. Sorry, right? Okay, let's try to come up with the reactions happening here, try to come up with the redox reactions possible here, right? Okay, first concern about the thing adding from the top, the foreign reagent, what it will do, right? Okay, so we can say this is actually, you have 2 of K pluses and CrO4 2 minus sign, right? That is the potassium dichromate is the combination of those two things, right? Okay, and what we know is actually the K plus as a S block ion won't participate in redox reactions, right? So then but which the ion participating in this reaction, if this redox reaction, is actually the dichromate ion. So dichromate ion, what it does, right? Basic dichromate in acidic medium, note says will go towards Cr3 plus, will go towards Cr3 plus. That is kind of a reduction. Right? So with the dichromates, the oxygen state is going to be +6 with one chromium, right? So with the chromium, here is the plus 3, right? So it's kind of a reduction, right? From the top, you are observing a reduction, right? That means it should be an oxidation occurring at the flask. It should be an oxidation occurring at the flask. For this guy to reduce, to get this guy to absorb electrons, there should be something which will release electrons. Kind of oxidation should occur at the flask there, right? Let's see which guys are going to react here, right? The point is what? The point is, again I am telling you, if some species is with its highest oxygen state available, then such a species can't get oxidized. Can't get oxidized. Can't get oxidized. So if you are with your highest oxygen state available, such a species can't get oxidized, right? So when we are referring to these two guys, what are the oxygen states here? With the sulfate, sulfur's oxygen state is +4. Right? Sulfur's oxygen state is +4 with sulfate. Sulfite. With sulfate, its oxygen state is +6. Sulfur's oxygen state is +6. Right? So +6 is the highest oxygen state of sulfur available. When we are referring to the oxygen states of sulfur, right? +6 is the highest oxygen state of sulfur available, right? So that SO42 minus here can't get oxidized. So SO42 minus can't get oxidized. Can't get oxidized, right? The idea is clear, no? If you are with your highest oxygen state available, you can't get oxidized, right? So then what will happen? But as the sulfite is not with its highest oxygen state, sulfite can get oxidized to the sulfate. But the sulfite will oxidize to sulfate. So the sulfite ion will get oxidized to sulfate here, right? The idea is clear, no? So the +4 oxygen state of sulfite get oxidized to +6. Right? So let's write the reaction here. So let's try to write the reaction here. So if you're trying to write the reaction here, the reaction is going to be in acidic medium, dichromate ion Cr272 minus ion reacts with the sulfite ion to produce the Cr3 plus and this guy oxidizes to sulfate. So this is the reaction happening. So you need to balance this thing with the use of redox techniques. Right now, this is how we are supposed to come up with the redox reactions. Right? You have to select which reactions to occur and then you have to write the products as well. You have to write the products as well. Right now, this is the idea. Right? If some species is its highest oxidation state, then such a species can't get oxidized. That is what we are discussing here. Right? That is what we are discussing here. Right? Okay. Let's consider another example. The other way around. Right? So let's copy this one. So again, another example. Right? Let's say you are with a Fe2 plus ion and a Fe3 plus ion. Another example. Right? Let's say this guy is with some X moles. This guy is with some Y moles. Right? Okay. You are adding some acidic medium Ki. Acidic medium more. Some excess Ki. Let's say X6 Ki. Right? So you are adding some excess Ki here. Right? Excess Ki means the K plus and the I minus, right? Okay. Let's see what reactions are possible here. Right? Okay. First of all, look for the reagent which you are adding. Actually, the foreign reagent, right? So here the K plus won't participate in redox reactions. Right? S-redox species won't involve in redox reactions as ions, right? So then I minus. So always the halogens as products prefer the X minus form or the X2 form. It will produce only the X minus form or the X2 form as products in these redox calculation procedures, right? So the I minus, as this is the X minus form, will form the X2 form, the I2. That is the only possibility for the halogen, right? As products, always X minus form or the X2 form should produce, right? So in this case, the minus 1 oxidation state of iodine had converted to 0 oxidation state. Right? So it is kind of a reduction. Sorry, it's kind of oxidation. Sorry for that. Minus 1 goes to 0 means it's kind of a oxidation. So only a reduction could be possible here. Only a reduction could be possible at the flask. This guy to get oxidized, there should be someone to accept those electrons. This guy to release some electrons, there should be someone to accept the electrons, right? So we are thinking of only a reduction at the flask, right? So now again we can apply the same theory. What is theory? If a chemical species is with its lowest oxidation state available, then such a species can't get reduced. Can't get reduced. Right? If you are with your lowest oxygen state available, there is no other low oxygen state to get reduced. No? Reduction means you are trying to reduce your oxygen state, decrease your oxygen state. Right? So, if you are with the lowest oxygen state available, then there is no place to get reduced, no? As you are with the lowest oxygen state, right? There is no such oxygen state to get reduced, no? So, if you are with the lowest oxygen state available, then such a species can't get reduced. Can't get reduced. So, in this case, as we know, the iron is available with only the +2 or +3 oxygen states. So, the Fe2 plus is its lowest oxygen state. That means Fe2 plus can't get reduced. Can't get reduced. So, Fe2 plus cannot get reduced. So, no reduction with the Fe2 plus. No reduction with the Fe2 plus. But there will be a reduction with Fe3 plus, right? But Fe3 plus will reduce to Fe2 plus. Some low state available, right? So, this is the reaction. There Fe3 plus will reduce to Fe2 plus, right? It's a reduction. So, what is the available reaction here? The available reaction here is actually then when the I minus reacts with Fe3 plus, I minus is reacting with Fe3 plus, and I minus get oxidized to I2 while the Fe3 plus get reduced to Fe2 plus, right? That is the reaction possible here. So, you can balance the reaction with the use of redox techniques. Idea is clear, right? That is how we are supposed to, right, predict the redox reactions, right? Let's see another thing here, some another example, right? I'll give you another example, right? Right? Right, let's say you are with, right, some IO3 minus, right, and some IO3 minus and some S2 minus appearing here, IO3 minus and some S2 minus appearing here. Let's say this is with X moles, this is Y moles, right, and you are adding some I minus from the top, Ki, let's say Ki, right, you add in some Ki from the top, Ki means Ki plus and the I minus, right? Okay, let's decide the reactions which could occur here. So, as is look ion, K plus is not going to participate in this reaction, and the I minus, the only possibility there is for I2 to get oxidized to I2 I minus 2 get oxidized to I2, right? So oxidation state here is -1, here is 0, right? Okay, that is kind of oxidation. So we are looking for only the reduction at the flask. We are looking for only the reductions at the flask, right? Okay. But when considering this thing, right, sulfur is actually with the -2 oxidation state here. This iodine here is with +5 oxidation state. Sulfur is with the -2 and the iodine is with +5 oxidation states. And you clearly see the sulfur is with its lowest oxidation state, right? Sulfur is with its lowest oxidation state, right? So sulfur is not going to react, right? Sulfur is not going to react. So I'll give you some hint, Lama. I'll give you some hint. So actually, when it comes to p block elements, as they are showing some variable oxidation states, right? There is a shortcut method to come up with the highest and the lowest oxidation states available with those, right? Normally, right, when the p block metals are concerned, their highest oxidation states available and the lowest oxidation state available can be taken like this, right? If you are a right group 16 element, if you are group 16 element, your highest oxidation state, highest oxidation state is actually +6, which is the number of electrons at your valence shell, that will give you the highest oxidation state. Your lowest oxidation state is actually -2, which is the number of electrons required to complete the valence shell, right? It's the number of electrons required to complete the valence shell, right? So this is the right number of electrons in the valence shell (6) is that, right? 2 is actually number of electrons needed to complete the valence shell, right? Like that, you come up with the highest and the lowest oxidation state of p block nonmetals, right? So basically, those are the two methods available to come up with a complete outermost shell. Right? By releasing 6 electrons, by releasing all the electrons, right, you can come up with a complete outermost shell. Releasing electrons means plus 6 electrons are there at the outermost shell for the sulfur group 16, right? So releasing all the 6 electrons of your outermost shell can come up with a complete outermost shell, right? Shell, right? So this is the other method, right, which is actually, right, you can gain 2 electrons, to complete the shell, right? So those are two methods available, right? Let's discuss the same idea with the group 17s as well. For the group 17, elements, the highest oxidation state then, right, number of electrons you need to release to come up with a complete shell. That means you can release all the 7 electrons at your outermost shell to come up with a complete shell there. So that is the +7. You can release all the electrons at the outermost shell. So that is actually the number of electrons in the valence shell as well, right? So lowest oxidation state is how many neutrons you need, to complete your shell, that is -1, as 7 neutrons are there at your group 17 elements, so at the valence shell, right? So 1 neutron is sufficient to complete its shell, right? So +7 to -1, that is oxidation range for group 17 elements, right? So for group 16 elements it is the +6 to -2. So that is some method to come up with the highest and the lowest oxidation states available for group 6 for the p block nonmetals, right? Okay, so you can use these theories as well here to identify which guy is to react and which is not, right? So anyway, with sulfur as a group 16 element, it is lowest oxidation state is -2. So if you are with the lowest oxidation state available with you, you can't get reduced, you can't further get reduced, right? So no reduction with the sulfur, right? Okay, so right, we can say, so no reduction possible with the sulfur, this 2 minus, right? What about the IO3 minus? Iodine as a group 17 element, its lowest oxidation state is not going to be the +5. It is lowest oxidation state is not the +5, right? So it can get reduced. It is not with its lowest oxidation state, so that it can get reduced. So that IO3 minus can get reduced. IO3 minus can get reduced. That +5 oxidation state can get reduced to air. The iodine is supposed to get reduced. So basically, as products, always the halogens prefer the X2 form or the X minus form. Right? So here, when it comes to the numerical scale, right? When it comes to numerical scale, right? -1, 0, right? +1, +1, the +5 is now there, right? +3, +5, those are the normal oxidation states available with the halogens, right? +7, right? So now you are here, right? So when you are to get reduced, first you will come up with 0, right? Not the -1. So first you will come up to the X2 form, right? So if they have not given any products, so you are supposed to reduce to the 0 form, the X2 form, right? X2 form and the X minus form are the availabilities now. So first you will come up with the X2 form now when get reduced. So just write the X2 form there, right? So that is actually the I2. Right? That is actually the I2. So that is the reduction possible there. So now we can come up with the total reaction here. So what it could be the total reaction here, right? So I'll write it as acidic medium reaction. X is acidic thing, is it, right? Right. So the reaction is going to be then the acidic medium reaction. What happens? Your I minus reacts with the IO3 minus here to produce the I2. The I minus will get oxidized to I2, while the IO3 minus get reduced to I2, right? So this guy will get oxidized to I2, and the other one get reduced to I2, right? Anyway, that is the redox reaction possible with this system. Got the idea? Right. Okay. So now I think you have some idea to select which reactions are to occur or not with the redox systems, right? So we'll use this knowledge to come up with some chemical calculation, right? Let's go to this. Right. Okay. Let's come up with a chemical calculation, right? Question. Okay, now let's try to solve this question. This is a question actually involving the redox reactions as well as the precipitations, right? Let's try to do this one. This is the 2006 A-level question, right? Okay, let's try to solve this one, right? So we are actually following the normal procedures, right? Normal solving techniques, right? First thing is actually to come up with the goal, right? So first thing is to find out the goal, right? So what is the goal of this question? Right, identify the goal, right? So the goal of this question is actually calculate the concentrations of SO3, it's 2 minus, right? So SO3 2 minus, right? SO3 2 minus and the right C2O4 2 minus. Just change these things, right? So calculate the concentration of SO3 2 minus and the C2O4 3 minus, right? So that is what we require to find here, right? Okay. So first put the X moles and Y moles for the species of your goal, right? So you can write let the SO3 2 minus is equal to X moles and C2O4 2 minus is equal to Y moles, right? Okay. So we have a problem here, right? Right. These are at 25 cubic centimeters of the solution, right? Right. Identifying the goal. That step is done. Now, after that, we are supposed to come up with the chemical reactions involved in this procedure. Chemical reactions involved in this procedure, right? What are the chemical reactions? First thing. So you have the solution B here, right? You have the solution B, right? There you have the SO3 2 minus signs as well as the C2O4 2 minus signs, right? So we had taken 25 cubic centimeters of this solution, right? Then we had taken this as X moles, this as Y moles, right? Okay. So to this one, they have added 0.05 molar Km of solution. They have added some Km of solution from the top, right? Km solution is added in the acidic conditions, right? In the acidic conditions. So they have added some KMnO4 in the acidic conditions. So KMnO4 means K plus and the MnO4 minus, right? Okay. The amount of that thing consumed is 40 cubic centimeters from 0.05 molar, right? 40 cubic centimeters were consumed from 0.05 molar solution, right? Let's try to solve this one. Right, first thing to consider. First you have to select the reactions which will occur here. So first think of the reagent you are adding from the top. So it's K plus, it is not going to react, right? S block guys won't participate in these reactions, right? Redox reactions. So K plus not going to react. So with the MnO4 minus in acidic medium, it will always get reduced to Mn2 plus. Get reduced to Mn2 plus. So that is kind of a reduction, right? Mn4 minus converted to Mn2 plus is kind of a reduction, right? So we are thinking of oxidations. We are thinking of oxidations in the flask. We are looking for some oxidations in your flask, right? The idea is clear, right? Okay, then, so as Mn4 minus reduces, we are looking for some oxidations in the flask. Now you have to select, right? SO4, SO3 2 minus. Can it get oxidized? Is it with its highest oxidation state available? No. The highest oxidation state of sulfur is actually plus 6, but here your sulfur is with plus 4 oxidation state, right? It is not its highest oxidation state available for the sulfur, so it can get oxidized. So there is a reaction with Mn4 minus and the SO3 2 minus. What about this thing, the oxalate? With oxalate, your carbon is with plus 3 oxidation state, right? Your carbon is with plus 3 oxidation state. That is not the highest oxidation state of the group 14. With the group 14, the highest oxidation state is plus 4, right? Number of electrons you can remove to come up with the noble gas definition of the earlier noble gas, right? So that means plus 4, as you are with 4 electrons at the group 14 valence shell, you can release 4 electrons there. So plus 4 is the highest oxidation state of carbon, but that is not the value appearing with the oxalate, right? So this guy can also get oxidized, right? So both the guys will get oxidized with the Mn4 minus ions, right? So both are participating in the reaction, right? So let's write the reactions there, right? Coming up with the chemical equations here. So bound reaction is an acidic medium balancing, right? Mn4 minus reacting with SO3 2 minus to produce the Mn2 plus and what? SO4 2 minus. This clear now? The sulfide guys will get oxidized to sulfates. That is what it says with our note, right? So the other reaction here is in acidic medium. The other reaction is your Mn4 minus ions reacting with the C2O4 2 minus ions to produce what? The Mn4 minus reduces to Mn2 plus, while the C2O4 2 minus ions will oxidize to CO2. In your note, that is also given, right? In acidic medium, oxalates will oxidize to CO2, right? Let's balance this stuff. Let's balance this stuff with the use of techniques we have learned. So I am going for the straight balancing technique, right? Let's do this stuff, right? Balancing. So if you consider oxygen states here, this is plus 7, right? This is plus 2. So 5 electron difference. So here you see 5 electron difference, right? This is plus 4, this is plus 6, so that you are with 2 electron difference there. So least common multiple is actually 10, so you need to multiply this thing with 5, right? 5, and this half with 2 to come up with 10 as the least common multiple, right? Then balancing of H pluses and the both additions, right? So balancing charge, minus 2 is there, minus 10 is there, altogether minus 12 at this side, and this side, that side minus 12, and this side the net charge is minus 10 is there, plus 4 is there, so minus 6, minus 6. So you would see, right, 6 units of difference, right? So here, sorry, here the minus 12, sorry, minus 12, and minus 6 units of difference. So you need to add 6 of H pluses here. So to balance the stuff, you need to add some hydrogens, so 3 of H2Os. That is how you are supposed to balance the reaction of Mn4 minus with the SO32 minus, right? That is correct, no? Right. Let's balance the Mn4 minus with the oxalate thing, right? So I'll get rid of these. Right? The clearness of your answer, right? Okay, no need of these things now. Right. What about this? Let's try to balance this second reaction as well. Right? First come up with oxygen states. Here, this is +7, this is +2. So 5 electron difference with this one. First of all, you need to balance the redox atom, so that you need to come up with 2 here, as 2 carbons are appearing. Right? Here the net oxygen state is going to be +6, so -8 is there. So +8 minus 2 is +6. Here 2 carbons is +4 means +8. So 2 electron difference there. So this needs to be multiplied by 2, as least count multiple is 10. And this needed to be multiplied by 5. So 5 here and some, it is becoming 5 into 2 is 10, right? 5 into 2 is 10. Right? So now the charge balancing, -2 is there, -10 also again -12 at this side, and this side you have +4. So altogether 16 of difference. So 16 H pluses and some 8 H2Os here. Right? That's how the two reactions are balanced, right? So I'll get rid of these things, right? Right? Right now? So those are the two redox reactions here. So coming up with the chemical reactions, right? That is what we have done here. So now it's the time to come up with the simultaneous equation for this procedure, right? So as you are with X moles here and Y moles here, right? This amount is going to be, right? X means for 5 portions, so we need such 2 portions. So X means for 5 portions, we need such 2 portions. This is the number of moles of Mn4 minus related with the sulfide, right? So Y means for 5 portions, we need such 2 portions, right? So Y over 5 into 2, right? So we can come up with the first simultaneous equation from this one, right? First simultaneous equation from this one. So that will be written for, this thing, right? So let's write for the moles of KMnO4. For the moles of KMnO4. For that we are writing the simultaneous equation here, right? So let's write. So KMnO4 moles is actually equal to 40 cubic centimeters with 0.05 molar, right? So that is 0.05 moles per cube, 40 cubic centimeters. So 14 × 10⁻³ right. So the value is then right, you have 2 × 10⁻³. 2 × 10⁻³. So in terms of x and y, you can write the 2x over 5 plus 2y over 5 is equal to, right, that is our equation here. You can write 2y over 5 is equal to 2 × 10⁻³, right, for the moles of K in a form, right. So if you complete the linear form, we can write 2x plus 2y is equal to 10 × 10⁻³, that is 0.01. That is equation number 1, right. Got the idea, no? Okay. So as to solve for two unknowns, basically we need two simultaneous equations, right. Now we had come up with one simultaneous equation like this, right. Let's come up with the second one, right. Let's come up with the second one with the use of this precipitation data, right, with the use of precipitation data, right. Okay, let's come to that stage, right. So what they are saying? They are saying the resultant solution was treated with excess of BaCl2. So let's come up with the resultant solution. So the resultant solution looks like this, right. What are the things at the resultant solution? See, right, from this reaction you had produced some sulfate ions, right, and Mn2 plus ions, right. Those are the ions in the solution after this reaction, right. So resultant solution contains Mn2 plus ions and the sulfate ions. The CO2 will be liberated as a gas, right. Okay, so S ions, Mn2 plus and sulfate would be there, right, in your resultant solution, right. So you have SO4 2 minus ions and the Mn2 plus ions, right. This is your resultant solution. And what are the amounts? We need to come up with the amounts as well, right. So the sulfate amount is same as the sulfite amount, right. Sulfate amount is same as the sulfite amount, right. That is also the x moles, right. Right, x moles of sulfate is there, right, 1:1 ratio. So we can write that, right, this amount is x moles, right. To this thing you have added some excess of BaCl2. You had some excess of BaCl2. Excess of BaCl2. That is Ba2 plus ions and the Cl minus ions, right. And they had observed some PPT. Precipitate is observed, right, and its mass is what? 0.466 grams, right. Okay, so let's consider the reaction here. Let's consider the reaction occurring here, right. Sulfate with BaCl2. Let's select with the use of precipitation techniques available. So basically no cation available here, so no need of thinking of the Cl minus here, right. Okay, no need of looking for Cl minus here. So what you have here is Ba2 plus signs. So you need to consider the Ba2 plus signs with the sulfate times here, right? As the manganese chloride is not a precipitate, right? Manganese chloride is not a precipitate, right? So what you need to consider is the Ba2 plus signs with the sulfates, right? So let's write the precipitation reaction here, right? The reaction is then BaCl2, right, reacting with sulfate times. What should happen? So basically the cation anion will connect to form the barium sulfate. That is actually your precipitate, right? And this 2 of Cl minuses will release, right? No? So that is the idea, right? So you are with some X moles here, so that the number of moles of barium sulfate should be also X moles, right? No? 1-to-1 ratio. So now we can come up with the second simultaneous equation, right, using this data point of precipitate mass, right? So let's write for that. For the mass of barium sulfate precipitate in terms of grams, right? So when it comes to barium sulfate, its molar weight is equal to, this is 137, sulfate is 32, and oxygen, 4 of oxygen, 16 into 4, that is 64. That will add up to give you 233 G mole minus 1, right? So the weight of barium sulfate precipitate is the molar weight G mole minus 1 value with the mole value, right? So that will give you 233 into X. That value is equal to what? The mass given here, the data point, 0.466 grams, right? No need of writing the grams, right? So it means 466. So this will give you the X as 0.002. So that is your second equation, and solving for the X, right? X is equal to 0.002 moles, right? So now we have built up the two simultaneous equations, right? Now we can use these two simultaneous equations to solve for X and Y, right? Now, so let's solve for X and Y, right? Solving simultaneous equations. What were the two equations, Laman? Right, the first equation was like 2x plus 2y is equal to 0.01, right? 2x plus 2y is equal to 0.01, that was the first equation. The second one was like x is equal to 0.002, right? So by solving from 1, we can take the y value as, right, so 2x, 2 of x means, so x is equal to 2.02, no, right? So 2 of x means that is 0.004, so 2y is equal to 0.006, so y is equal to 0.003, right? This is in moles, right? Right, these are the two values for the x and y, so that we can copy the concentrations, right? X is for the sulfide, this is for oxalate, right? So we can write the concentration of sulfide is equal to the amount of moles is this amount, it is 2 into minus 3, and the volume here is actually 25 cubic centimeters, no? 25 cubic centimeters. So these two will cancel off, 2 over 25, that means 8 over 100, that is 0.08. Right? If you are looking for the concentration of C2O2 minus ions, that is actually number of moles of C2O2 minus is 0.003, that means 3 into 10 to the power minus 3. The volume is 25 into 10 to the minus 3, the same volume, right? So the idea is that these things cancel off, right? 3 over 25 means 12 over 100, that is 0.12. So that is the concentration, right? That is how we are supposed to solve this kind of question. So this was a question involving both the redox reactions as well as, right, precipitation, right? Got the idea, right? See how we are supposed to use the redox reactions in this kind of calculation, right? So this was the first idea, right? So this is how we have selected the reactions possible here. In this case, both are possible. So like that, we had solved the question using the normal technique, right? First coming up with the goal as x and y, then writing the chemical reactions related to the procedures. So as the manganese here is going to reduce, some oxidation could occur at the flask. Both the guys will get oxidized, as those both are not with their highest oxidation state, right? So we need to come up with the two equations there. So we use the redox balancing techniques, right, to write the equations. After that, for the data point of came in a form out, we had written the simultaneous equation, right? Then we went for the next part of the question where they have discussed about precipitation. So there also we had selected which guys are to get precipitated, right? With the use of that, we used the write the chemical equation, right? And then we had come up with the second simultaneous equation for the mass of the precipitate, and by solving the two simultaneous equations, right, we had came up with the x and y values, which are the number of moles of sulfite and the oxalates, and then we had be able to come up with the concentrations of those two guys, right, with the initial fast as those guys are with 25 cubic centimeter solutions, right? This is how we are supposed to solve this kind of a question, right? So let's wind up at this stage, right, with this question, right? You can do the question number 2 and 3 as well, which are appearing in your page number 25 of your tute, right? Just do those things and as your homework, right? So let's wind up at this stage. See you at the next class. Goodbye then.